Yes, yes.
Okay, perfect. Thank you very much, Massimo. Thank you very much for the organizer of the event. So yes, I'm going to speak about. This is a distraction from machine learning and the current revolution that we have to face. But this is also a topic that many people in machine learning are actually playing with. Still, this is really within the confine of a variational data assimilation and using new metrics that are in the air and see what we can do with them. Okay, those are the co-authors of this work. So at first, I'd like to motivate why we actually want to look into using optimal transport and some of the metrics that we can derive from optimal transport. And one of the motivation is some of the weaknesses that we have in classical data assimilation. The first one being, for instance, the requirements of strongly overlapping priors that we have in classical data assimilation, yielding small increments. And the other one is something which is really ubiquitous in many areas of the geosciences, is the double penalty error. That is also now present in the machine learning emulators of weather, for instance. So this is something that is a recurrent theme in the geosciences and in data simulation as well. So those are two illustrations of those kind of weaknesses, and the first one being the double penalty error, where we see the truth, which is the location of one field or one puff of pollutant, for instance, in one grid cell in red. And the analysis, or the estimate of this of the location of this puff is actually this green grid cell here. And you see that those two increments using root mean square error, for instance, will give exactly the same value. But actually, you don't really predict the same thing, and you'll be very much happier with the first increment rather than the second one. So there's something wrong here that does not translate in the metrics that we've chosen here. And the second one is this here, the illustration of the overlapping fields. So be careful; those are not PDFs or distribution; those are actually fields. Okay, I will speak about distribution, but those wouldn't be probability distribution, but other fields. And those are typical fields, typical two puffs of pollutants. And in red, it will always be the observations. In blue would always be the prior, so the background. And in green would be the analysis. So we typically look for that kind of analysis. And there the assumption that we don't know exactly, but we know that there are some location error on the puff. This is the typically kind of things that of analysis that we could end up with on the right, and this is really not what we'd like to do. We'd like to have something in the middle, finding the compromise in terms of assuming that we have location behind the scene. Okay, so before getting back to data assimilation, I'd like to mention the fact that this issue of choosing the right metrics is actually a topic that has been discussed, especially in the field of verification. And there's been a few proposals of using different metrics to verify fields in many areas of geosciences. And there's been scale-dependent metrics. There's been metrics based on the object or feature derived from the classical fields. There have been indexes from the machine learning community and computer vision, for instance. There have been this concept of warping the fields and then applying more classical metrics. And the last class of method is the Wasserstein distance, which is really a distance in the mathematical sense, which is based on the theory of optimal transport. So this is a slightly more theoretical, but this is also on safe mathematical grounds, because there are a lot of works from applied mathematicians in this area that we actually can leverage. Okay, so I'm going to give you a brief overview of what optimal transport is and what is the definition of the Wasserstein distance. So this is an old problem that was an engineering problem initially, where we have a distribution or pile of sand or rubble that we would like to move into an embankment here, And so this distribution rho, I mean, has to be moved to this rho B. And moving, you know, a piece of Earth actually has a cost, and which is defined by the CBO. And you can define the distance between those two distributions or those two fields by this formula, which is so the square of the Wasserstein distance, and is given by the optimal transport. I mean, the one that is that costs the least costly. So in between, so moving from rho 0 to rho B. And of course, you have to minimize over all the admissible transport, those that actually preserve the density, preserve the mass. Okay. So one of the constraints here is that we have to require that the mass of the origin distribution is the same as the mass of the target distribution. That's something we have to keep in mind. This is one of the constraints that we have to deal with and actually circumvent at some point, because this is not something that we'd like to have in data assimilation. Now, so as you've seen, the definition is actually very simple, but it's deceptively simple in the sense that solving mathematically this problem is really not that easy. The concepts are not that easy. The formulation itself seems easy, but the concepts are not easy. And there's been an improvement and or some kind of extension of those concepts in the 20th century by Kantorowicz, and he has developed this probabilistic view on the optimal transport and the definition of the Wasserstein distance, which wasn't called the Wasserstein distance at the time. But it's instead of having this disymmetric or asymmetric view from the origin density to the target density, you consider them as the you don't introduce the deterministic transform map T, but rather you introduce transfer plan, so some coupling, which is a probability distributions that couples actually the origin of the target distribution. Okay, so this is the bilinear, not bilinear, but a B. I mean, this is the distribution of two variables or two density x and y, and this leads to this definition of the Wasserstein distance. This is actually the same as the one before, except that now it's formulated in terms of transfer plan pi, and now this is symmetric, and this is why it's so nice. It's symmetric in the origin of the target density. And now the admissibility constraints now is implemented as the fact that the marginals of this transfer plan has to be the origin and the target densities. Okay, now, so we're on data assimilation and geophysical data assimilation. So we tend to discretize our problem because we want to implement and test them in a computer. And so let's write those formula. And actually using this transfer plan formulation, this probabilistic formulation by Kantorowicz, in terms of discrete variables and discrete vectors. So now the distribution, so not necessarily a probability distribution, but it could be a field, are what we call probability vectors. Okay, but they are, think of them as fields. And those are, so the origin distribution, or the origin vector and the target vector, xo and xp. And I'm assuming that their same is their mass is the same. Doesn't have to be one actually, but the important thing is that they need to have the same mass. Okay, and if you write down the Kantorowicz coupling, and this is why this is so elegant, you end up with this simple formulation. This is just the a scalar product between the transfer plan and the cost of moving all those bits of mass. And this is under the constraints again that the coupling satisfies these marginals xb and xo. Now this is not necessarily a convex problem. Okay, this is the formulation is simple, but this is not so easy actually to solve. And one elegant way to solve it approximately is to regularize using an entropic regularization. And here I'm choosing to have the Kullback-Leibler divergence to the cost function, so to the cost that we're computing with this trace of matrices. And so we're just adding with a small coefficient epsilon this Kullback-Leibler divergence. And this has the merit of actually convexifying the problem. making the solution simpler to compute and guaranteeing that we have a single solution. Okay, and that's this actually solving this in one very classical way to solve this is leads to the so-called or yields the so-called synchron algorithm. So this is something we've used, but this is not what I'm going to show today. Okay, now going back to data assimilation. So I'd like to mention a few attempts to use actually optimal transform in data assimilation. And so to use the non-local matrix, first of all, not necessarily related to optimal transport, but something very similar. So there's been displacement data assimilation or multi-scale combined with displacement data assimilation. And then there's been really the use of optimal transport technique and the Wasserstein distance in to assist actually data assimilation and maybe some ensemble forecast. And many of those works are actually quite recent. So it has been used for ensemble post-processing, or it is actually being used for ensemble post-processing. It has been also on a more theoretical level, it has been used as a flow formulation within the flow formulation of the analysis update in data assimilation. It has been used also in ensemble data assimilation. But I like to stress the fact that in all those works, I mean, there's been it has been applied to the PDF of the fields, okay, and also that comes with the curse of dimensionality, meaning that usually we don't. I mean, people can't really go beyond looking into one or two or three variables. So those works are not related really to the fields, but there have been a string of very nice. Work initiated by Arthur Vidar, Maël Naudet, and at the time PhD student Nelson Fayeux, who actually try really to apply combined data assimilation on optimal transport and apply that to fields. So meaning that the fields would have to be distribution, meaning that we are interested in non-negative fields. So typically pollutant or whatever, vapor or any fields of this type. So I'd like to stress for the last time that here I'm going to focus on those fields, on using optimal transform data simulations on those fields, and I'm not using optimal transform for as a probability distribution, a tool to work on probability distribution. Okay, so what do we do if we want to apply optimal transport in data simulation? So you just consider the this is typically a 3D var. This is what I'm going to focus on here. And with the X will be the future analysis that that I wish to find, and Y not will be the classical observation, and YB will be what we usually call XB, the prior, the background. But for a reason that I'm going to explain later, it's actually now think of the Y as being all the information that you put into the data simulation system, and that's why there is this switch in notations that I think is very convenient ultimately for introducing optimal transform in data assimilation. And now so this is just 3D var, and just substitute the Euclidean norm with the Wasserstein distance, or the norm of the Wasserstein distance. And this leads to this 3D var cost function, this generalized 3D var cost function. So it seems nice, but when you look into it, you realize that actually it requires the mass of what you would actually forecast or predict from the analysis would have to have the exact same mass as the observations. And this is where this is actually conceptually not what you really want, because this implies that you would try to find the analysis where the support of the observation operator is. So meaning that you would like to find your keys under the street light. So this is not exactly the kind of analysis that we're looking for. And this is illustrated on the left. So this is really solving this numerically, this problem with these only 1D problems with again, those in red, this is the observation, in blue, this is the prior, and the analysis is in green. And the observation support is only on this wavy line on the left of the domain. And you see that the analysis actually found, where the observation operator here is. This is not what you're looking for. We'll be looking more like something like on the right, which is solved using the theory that I'm going to introduce. So this this problem was actually really described by Nelson Fayeux at the end of the PhD studies, and this is maybe one of the obstacles that they found at the end of this stream of work. So what are the assumptions that I'm going to make in the following? So I'm going to really assume that I'm looking into fields and non-negative fields, and I'm working with them. They won't necessarily be first. Well, so let me say that I'm going to use the fact that I will assume that the observation operator to be linear, but this is not really that constraining. This is just a convenience here. I'm going also to assume the convexity of the negative log probability of the error statistics. So this is just a way to formally write all the statistics, the error statistics for the background and for the observation here. And Gaussians are, of course, in this family of distributions. So this is not a very hard constraint. And I won't have to assume that the mass of the priors actually are the same. So that the mass of the observation and the mass of the background of the first guess actually they don't have to be the same. The parameter can be unbalanced. Okay, so we will circumvent the issue that is usually raised when using optimal transport. And I'm going to try to reproduce what would be the 4-divar-like analysis. So using this combined optimal transport or net assimilation, so ETDA in the following. So the idea is actually to replace the, so on the left, this is the diagram corresponding to classical 3-divar. And on the right, this is what we will actually do. So we will replace and so the idea is actually to work in the state space rather than in the observation space. And in the state space, we are going to define those objects XB and XO, which are actually the states corresponding to the priors. Okay, YB and YO. And the analysis will be defined as some compromise, some barycenter between this XB and XO, which has to be fine, like as part of the analysis. So usually in optimal transport, people say that XA would be defined as a Wasserstein barycenter between XB and XO. And if you write the corresponding cost function of OTDA cost function, this leads to this cost function. So it's slightly different one than the one that has been proposed by Feyeux. And but this is now, there are two Wasserstein distance. So in between XB and XA and XA and XO. And there are the classical error statistics that we have in 3-divar for the background and for the observations. And this essentially solves the, as we will see, the critical issue that has been raised by Feyeux. Okay, so I'm going to go through one way to solve it, conceptually nice way to solve it, which is actually quite enlightening. But at the end of the day, I will show a numerical example where I'm using a straightforward methods, which is much less enlightening, and that's why I like first to explain some of the concepts behind it. So one way to solve this and to minimize this 3-divar cost function is actually to simplify the problems, because we have those two Wasserstein distance. And so one way to simplify this is actually to, there is a way to actually shortcut this and bypass this and define an effective cost metric in between XB and XO. And this leads to much simpler problems with only one Wasserstein distance. But then the XA will be later diagnosed through some kind of interpolation, which is called the Malkan interpolation, but not in the value space, but actually in the physical space.
Mark, sorry to interrupt, but you've got 4 minutes.
Yeah. Okay. So there are mathematical ways to solve this cost function. And the way we chose here is to define the dual cost function for this. And this is very reminiscent of what is usually called the physical space statistical analysis system that we could use for 3-divar or 4-divar. So this is the equivalent of what we could use. So this is writing really the dual cost function to this 3-divar cost function, and using again this Kullback-Leibler regularization. And this leads to something which doesn't have to be minimized under constraints. So this is something that you can actually rather easily minimize. And this leads to this kind of solution, numerical solution. This is in 1D. So I don't really have time because you can spend minutes actually discussing this kind of diagram. But I like to show that you see the green analysis. This is the OTDA solution. but the orange one is actually the classical data assimilation that you would obtain with 3D VAR. And you see the differences depending on how large is the support of the observation operator. And this is, you see how this actually changed, and how maybe under location error, the OTDS solution would be more satisfying than the classical data assimilation one. And this is another illustration where you actually increase a lot the cost of the metrics that you use in optimal transport. And so this is from left to the right. And as you would hope and expect, actually the generalized OTDS solution converged to the classical data assimilation analysis. And this is indeed, and there you see that the green curves coincides with the orange curves on the right. So classical data assimilation is actually a limit case of this generalized formalism. Okay. Now, 3D VAR wouldn't be perfect if you can't really estimate also the uncertainty, and this is something that you can also do within this formalism. This is a bit more tricky, but you can write the normal equations as you would do with, you can do actually with, from classical 3D VAR. And this leads really to similar solution of corresponding to the 1D example that I've given. And those are, but now you've got error bars attached to the solution that you can derive. And finally, this is the typical 2D example that you can do the same. Okay, these are as a numerical cost, but there is no curse of the dimensionality per se. So then something really achievable. And you see that the classical solution and the OTDS solution are actually quite different. OTDS solution is much smoother as expected, is not so much impacted by the sparsity of the observations. Okay, so let me give you a few take-home message. There's the fact that we maybe solved or proposed a solution for the conceptual obstacle raised by Feyeux with this first attempt of using optimal transport and combine it with data assimilation and field. There's the fact that actually I haven't shown that, but the formalism is really rich. There's a lot of things that can be tested and tried. The fact that classical data assimilation is embedded in the formalism, which is something we like. Now there are things that we have started to explore, but not developed yet. There's the fact that there is a Bayesian standpoint on this OTDA formulation. There's the fact that there are also connections and a way to model the transfer plan, the counter-range transfer plan, and use stochastic matrix instead, which is also a nice thing. And there's a lot of discussion that we could have on we should have on numerics and how efficient those algorithms are compared to classical data assimilation. You can find a lot of these developments and many more examples actually in this preprint, and the paper is actually under review right now. Thank you.
Okay, many thanks, Marc. There was quite a dense presentation, and yes, I mean there are a couple of questions on the IOPAD, and I would also have a question myself, but I suggest, in the interest of time, if you could take them up offline and possibly answer them on the IOPAD, so that everybody can see. So thanks a lot, Marc.
Okay, thank you, Massimo.
Thank you.